Okay, in today's lecture, we're going to cover the section 11.9 material on continuity and differentiability. And we've already dealt with the concept of continuity and differentiability a little bit in this course, but we haven't seen the formal definition of continuity. So typically, up till now, when you've been thinking about a continuous function, you would describe it as a function whose graph consists of one smooth curve, or a curve that you could draw without having to lift your pencil. But let's make more precise this concept of continuity. So we would say that a function f is continuous at some point x equals a if the following conditions hold. Namely, number one, that f of a is defined, so the function is defined at x equals a. The limit of f of x as x approaches a exists. And condition 3, that the limit as x approaches a of f of x is equal to f of a. So that is, the function needs to be defined at that x value. The limit of the function must exist as we're approaching x equals a. And provided that both of those values exist, they must be equal to each other. That is, the limit of the function has to be equal to the value of the function at that point. Now, if f is not continuous at some point, say x equals a, we would say that f is discontinuous at x equals a, or that the function has a discontinuity at x equals a. And there are three different types of discontinuities that we could have for a function, which would be holes, jumps, or vertical asymptotes in the graph of our function. So let's look at an example of each of these. So an example of a hole in the graph of a function, let's say we're considering the part of some graph that lies in the first quadrant. We would say we have a hole at some point x equals a. If our graph is some nice smooth curve, but it's undefined at x equals a. So this fails the first condition for continuity. F of a is undefined here. Now the second type of discontinuity, a jump, might look something like this. So we would say that we have a jump discontinuity at some value x equals a if we have a nice smooth curve and maybe it changes its definition from one y value to another value at x equals a. That we would say we have a jump in the graph of our function. So here, the limit of this function would not exist as x approaches a, because we could see here that we would have different left or right hand limits. Now, another example of a jump would be similar to a hole. Let's say that our function is defined at x equals a. So this y value I'm sketching would be f of a. However, it's not equal to the value of the left or right hand limit of our function. In this case, we would say that we have a jump discontinuity, not a hole. So we only have a hole if our function is undefined at a given x value. And the third type of discontinuity is a vertical asymptote. So let's say that we have some nice smooth curve, but there's some value of x, say x equals to a, for which our function has a vertical asymptote. So it might look something like this. where as we're approaching x equals a from the left, our limit becomes infinitely large. So in this case, our limit does not exist. So now that we've defined these three types of discontinuities, or defined continuity more formally, let's look at some examples where, given the graph of a function, we can determine whether or not it is continuous at a point, and state what type of discontinuity we have if the function is discontinuous at a specific value. So here we are given the graph of a function f, and we're told to state the numbers at which this function f is discontinuous and identify the type of discontinuity. So looking at our graph, let's work from left to right along the x-axis. So moving left to right along this axis, it looks like the first point where we have a discontinuity is at x equals -5. So here at x equals -5, it looks like we have a vertical asymptote. The function is defined to be 0 at x equals -5, so it satisfies the first condition for continuity. However, the right-hand limit as x approaches -5 is infinite, and so our limit does not exist. It doesn't match the left-hand limit as we're approaching -5. So here we would have a vertical asymptote. Now, as we continue moving from left to right along the x-axis, the next value where it appears that we have a discontinuity would be x equals -3. It looks like we have a little hole in the graph of our function there. So at x equals -3, our function is undefined, so we would have a hole for the type of discontinuity. And as we continue to move from left to right, it looks like at x equals -2, again, we have a vertical asymptote. The function is defined to be 0 if x is equal to -2. However, the right-hand limit as we approach -2 is infinite. It doesn't match our left-hand limit. Therefore, we would say x equals -2 is a point of discontinuity because we have a vertical asymptote. So continuing to move along our x-axis, the next point of discontinuity would be at x equals 1. We have a jump discontinuity. So our function is defined at x equals 1. We see this closed point. However, the left-hand limit and the right-hand limit are not the same. Our limit does not exist as x approaches -1. So we have a point of discontinuity, which would be a jump discontinuity. Now continuing to move along, it looks like our next point of discontinuity is at x equals 3. Let's see, not -1 here, a +1 for that last point. We were to the right of our y-axis. Now for x equals 3, we can see again we have a jump. Our function is defined to be 0 at x equals 3. However, the left-hand and the right-hand limits of our function as x approaches 3 are not the same. Therefore, the limit does not exist. So we have another jump discontinuity. And as we continue to move along the x-axis, our next point of discontinuity is x equals 5. The function is defined at that point. However, again, the left-hand and the right-hand limits don't agree. So the two-sided limit, as we approach 5, does not exist. So at x equals 5, we have another jump discontinuity. Our next point of interest appears to be x equals 7. Our function is defined at x equals 7, but again, that left and right hand limit don't seem to agree. So at x equals 7, we have another jump discontinuity. And then our last point, where we have a discontinuity, appears to be at x equals 8. We see that we have a small hole in the graph of our function. So at x equals positive 8, we have a hole. So given the graph of a function, we can determine its points of discontinuity. We can look for points where either the function is undefined, has a vertical asymptote, or our limit does not exist. So we can extend the concept of continuity to a concept known as one-sided continuity. So let's define what we mean by one-sided continuity. So here, if we have a function f, we would say that function is continuous from the left at a point x equals a if the left-hand limit of our function as x approaches a is equal to the value of the function at a. So this really implies three things. First off, that f of a is defined. The function must be defined at whatever x value we're considering. The left-hand limit must exist as x approaches a. And if these two things exist, they must equal each other. That is, the left-hand limit must be the same as the value of the function at x equals a. So to illustrate continuity from the left, let's consider the graph of a function. So again, let's say that we're in the first quadrant of the xy plane, and we have some nice smooth curve, but we have a jump discontinuity at some value x equals a. So this function is not continuous at x equals a, but it is continuous from the left, because we can see f of a is defined, and as we approach x equals a from the left, the value of our function, that is our left-hand limit, is approaching the same value as f of a. So here we would have continuity from the left. Now we can consider a similar concept. We would say that a function f is continuous from the right at a point x equals a if the right-hand limit of the function is equal to f of a. So again, there's really three things that are implied here. The first is that the function is defined at x equals a. The right-hand limit of our function as x approaches a exists, and those two values must equal each other. So similarly, we could sketch a graph which is discontinuous but is continuous from the right. So if we had something like this, this would be a function which is continuous from the right at x equals a, because we see f of a is defined, and even though the left and right hand limits aren't the same, and we see a jump, the right hand limit as x approaches a exists, and it's equal to the value of the function at x equals a. Now, of course, if we have a function which is continuous at x equals a, that would automatically mean that it is continuous from both the left and from the right at that x value, because the left and right hand limits would both exist and be equal to the value of the function. So the left and right hand limits would equal the value of the function itself, and we would have continuity at that point. So let's consider another example similar to what we did in our last one, where we're given here the graph of a function f, And we're told to state the numbers at which f is discontinuous. And for each of those points of discontinuity, state whether the function is continuous from the right, left, or neither at that point. So for the graph of this function, again, let's move from left to right along our x-axis and state our points of discontinuity. So we see our first point would be at x equals -5. We clearly have a jump discontinuity. So at x equals 5, we have a jump discontinuity. And the question is whether this is continuous from the left, the right, or neither. Now we can see the value of the function at x equals -5 is this value. And the left-hand limit of our function is equal to the value assigned to the function at x equals -5. So here we have continuity from the left. Now our next point of discontinuity would be at x equals -3. We see again we have a vertical asymptote because as x approaches -3 from the right, our function is increasing without bound. However, at x equal -3, the function is defined, and the left-hand limit is equal to the value of that function. So again, we would say our function is continuous from the left at x equals -3. Now our next point of discontinuity is at x equals -1. We see we have a hole in the graph of our function. So at x equals -1, we have a discontinuity, and this is neither continuous from the left nor the right. So we see that our left and right hand limits do exist, and they're equal to each other, so the two-sided limit exists. However, the function is undefined at x equals -1. So if our function is undefined, the left or right hand limit couldn't equal the value of the function at that point, since it has no value assigned at that point. So here we would say neither from the left nor right. Now our next point of discontinuity is at x equals +3. We see here that we have a jump discontinuity. The value of our function is different from the left hand or the right hand limit. So at this point, x equals 3, our function is neither continuous from the left nor the right, since neither of those left or right hand limits is equal to the value of the function at x equals 3. Now, our next point of discontinuity is at x equals 5. We see we have a vertical asymptote, and our function is undefined at x equals 5. There is no closed point assigned to the graph of the function for x equals 5. So we have an asymptote, and since the function is undefined at that point, it can be neither continuous from the left nor the right. Now for our next value of x, we have a discontinuity at x equals +8. And we see that at 8, our function is defined, and the right-hand limit of our function as we approach x equals 8 is equal to the value assigned to the function at that point. So here we have a function which is not continuous, but is continuous from the right at x equals 8. Then our last value appears to be x equals 10. We see that we have a jump discontinuity in the graph of our function. And for this last one, our left and right hand limits are different. The two-sided limit doesn't exist. And we see that as we approach from the left and right, we have a hole in the graph of our function. That is, f of 10 is undefined. Therefore, this would be neither continuous from the left nor the right, since the value of the function does not exist. Now we can extend the concept of continuity a little bit further. So we've been considering continuity at a point, or continuous from the left or from the right at a single point. So we can now define what it means for a function to be continuous over an interval. So we would say that a function f is continuous on the open interval from a to b if the function f is continuous at every x value within that interval from a to b. So it's continuous on an open interval if it's continuous at every point that lies within that interval. And we would say that a function f is continuous on the closed interval a to b, so that is including the two endpoints, if f is continuous on the open interval from a to b and is continuous from the right at x equals a. So at our left endpoint, we have continuity from the right, and continuous from the left at x equals b. That is continuity from the left at the right endpoint of our interval. So again, let's consider the graph of a function, f, which is shown here. And we're asked to determine whether this function is continuous on some given intervals. Now our first interval in part A is from -2 to +1. So let's visualize that interval on the x-axis. So from -2 to +1, this open interval. So we see, looking at this interval, that our function appears to be continuous. We don't have any jumps, holes, or asymptotes. The only point that we do see a hole is at the right end point of our interval, x equals 1. However, since this was an open interval, we're not considering the endpoints. We don't include those endpoints. So for the interval -2 to +1, yes, this function is continuous over that entire open interval. Now in part B, we ask, well, what about the closed interval from -2 to 1? So if we now include our endpoints, well, we see that we have continuity everywhere from -2 up through +1. However, at our left-hand endpoint, we have a vertical asymptote. My graph appears to be increasing without bound. And at the right endpoint, we have a jump discontinuity. That is, the left-hand limit is not equal to the value of the function at x equals 1. So here we would say, no, this function is not continuous on the closed interval. It is not continuous from the right at the left endpoint, x equals -2, nor continuous from the left at the right endpoint, x equals +1. So let's look at another one. In part C, we're considering the open interval from 1 to 3. So here on the open interval from x equals 1 to 3, we can see that our function does appear to be continuous. We just have holes or jumps at the endpoints. But for an open interval, we're not including those two endpoints. So here we could say, yes, we do have continuity over that open interval. And again, looking at the closed interval from 1 to 3, so now if we include our two endpoints, we can see that our function is not continuous over that interval because it's not continuous from the right at x equals 1. We have a right-hand limit, which is different from the value of the function at x equals 1. And our function is also not continuous from the left at x equals 3, since the left-hand limit of our function is not equal to the value of the function at x equals 3. So in this example, we could say, no, this is not continuous from the right at x equals 1, nor continuous from the left at x equals 3. And then in our last part, part E, we consider the closed interval from 3 to 5. So on the closed interval from 3 to 5, let's see what we have. So we see here that our function appears to be continuous within that interval, and it's continuous from the left at the right endpoint, x equals 5, since the left-hand limit of our function as we approach 5 is the value of the function. And it appears to be continuous from the right at the left endpoint, x equals 3, since the right-hand limit as we approach 3 is equal to the value of the function at 3. So in part E, we could say yes, it does appear to be continuous over that closed interval. So let's consider an application of this one-sided continuity, or continuity in general. So here we're told to suppose that a smartphone data plan for heavy users charges $60 for the first 6 gigabytes of data, and then $20 for each additional 2 gigabytes of data or fraction thereof. So here we're told to let C of x be the cost in dollars of using x gigabytes of data, and in part A, we're asked to sketch the graph of that cost function over the x interval from 0 to 12. So here we have a vertical axis representing cost, C of x, and our horizontal axis is representing x, the number of gigabytes used. So we're told for the first 6 gigabytes, that is from 0 gigabytes used up through 6, the cost is a flat $60. So up through using that 6th gigabyte. Now, as soon as we pass 6 gigabytes and start to use a fraction of that next 2, so we were told for every fraction of an additional 2 that we use, the cost increases by $20. So at 6, we would have a jump in the price of an increase of $20. So we would jump from $60 to $80 for the next 2 gigabytes. So that would be from 6 to 8. So just to scale this, 2, 4, 6, 8, and then up through that 8th gigabyte. Then as soon as we start to use anything past 8, if we start to use a fraction of the next 2 gigabytes, we again have a jump in the price by another $20. So from $80 to $100 for the next 2 gigabytes. That is up through 10. And then as soon as we start to use past 10, we have another jump by $20 in our cost. And we would up through that 12th gigabyte of usage. And we can stop here because we were only asked to sketch the graph on the interval from 0 up through 12. So if we were to continue past this, we would see the same sort of $20 jumps occurring. So our graph here, of course, is discontinuous, where we have these jumps. So in part B, we are asked to find any points of discontinuity for the cost on the interval from 0 to 12. So here we can say the function c, or c of x, is discontinuous at the values x equal 6, x equal to 8, and x equal to 10. These were the three values of x where we saw a jump in the graph of our function. So a little justification. Here we had jump discontinuities. And then in part C of this problem, we're asked, is this function c, representing cost, continuous from the left or continuous from the right at the points of discontinuity that we found in part B? So that is at 6, 8, and 10, do we have continuity from the left or the right? So looking at our graph, we see that at 6, 8, or 10 gigabytes, the cost is defined as $60, $80, or $100. And our graph of the cost function appears to have a left-hand limit, which is equal to the value of the function at that point. Our right-hand limits, as we approach 8, 10, or 6, are not equal to the values of the function at those points. So here we don't have continuity from the right, but we do have continuity from the left. So we could say continuous from the left at each of these points, x equals 6, x equal 8, and x equal 10. Now, the last part of this section has to do with differentiability, and we've already discussed differentiability a little bit in section 11.4. So we had seen that there are three ways that a function can fail to be differentiable. If it has a sharp corner, if it has a vertical tangent line, or if it has a discontinuity at a point. So here we'll again mention this connection between what we've been talking about, continuity, and differentiability of a function. So recall this theorem that we saw in section 11.4, which says if a function f is differentiable at a point x equals a, that is, if its derivative at a exists, then that function f must be continuous at that same point, x equals a. Now, what we're going to make use of here, and what we used a bit earlier in chapter 11, was the converse of this theorem, which states that if a function f is discontinuous at a point x equals a, that is, if it is not continuous there, then it is not differentiable at x equals a. Because if a function is differentiable, it must be continuous. Therefore, if it is not continuous, it has no possibility of being differentiable at that point. So in this example, we are again given the graph of some function, And we're told to state whether the function shown here is continuous and or differentiable at the given values of x. So here in part A, we were given x equals -1. So shown, let's use a different color, shown here, x equals -1. And we see that our graph appears to have a corner at this point. So it is not going to be differentiable since it does have that corner. However, looking at the graph, it does appear to be continuous at that point. So we would say that this graph or this function is continuous, but not differentiable. At x equals -1. Now the next point that we're asked about is at x equals 4. So at x equals 4, we see that we have a jump discontinuity. Our function is continuous from the left, since the left-hand limit equals the value of the function. However, our right-hand limit is a different value. We see this jump occur. So we would say that this function is not continuous. And if a function is not continuous at a point, that implies that it's also not differentiable there. So here, not continuous and not differentiable at x equals 4. Now the next point we're asked about is at x equals 8. And looking at the graph of our function, well, f of 8 exists. We have a closed point, and it appears that the left and right hand limits as we approach 8 are equal. So the limit exists, and they're equal to the value of the function at 8. So here our function is continuous at x equals 8. However, we see this corner in the graph, this sharp edge. And anytime that we have a corner in the graph of our function, that means that it is not differentiable. And then our last point that we're asked about is at x equals 11. So at x equals 11, we can see, well, clearly our function is defined, and the left and right hand limits exist and are equal to the value of the function at that point. So this is a continuous function at x equals 11. However, it is again not differentiable because at x equals 11, we appear to have a vertical tangent line in the graph of our function. So here, again, we would say it is continuous but not differentiable because there we had a vertical tangent. All right.